recording on the session, so the session's being recorded. Okay, so good morning, happy Fridays. Let's actually let me go through and look a couple things. Let's see what I have. No, I just have these on here. All right, so I didn't make a list. I usually like to make a list of the types of problems, so maybe I should start with that. It's a good place to start. What do you say? Types of problems that we've had since exam 1. So I'll bring up, let's actually, maybe I'll bring up over here. I'll go bring up the schedule and take a look at it, see what we've covered. This is called Schedule B. Boom. And let's take a look, see. All right, so since exam 1, which was right here, and I think we actually had it on the correct date. And here's exam 2 that we're about to cover. So we did some stuff in chapter 4 where we did deflection and a little bit of introduction to FEA. So we used FEA with superposition to get the deflections and the homework in there. We also covered some buckling. These aren't really strong points of emphasis for the exam. That's in terms of my priorities. We can go over some problems. I don't think I'll ask any long problems. There might be a short problem related to these, so I just want to feel comfortable in doing a deflection problem. But I think even a superposition problem might take too long, longer than I want to allocate in terms of the exam. So we're mostly going to concern ourselves with chapter 5, right? So that's the majority of what's going to be on the exam. And inherent in that is the safety factors. We're not going to have to use any statistics, but I think that's a good thing to have done a homework problem on. We might have some. I think we will have some stress concentration on there, so be able to use the stress concentration figures correctly. Maximum shear stress theory, absolutely. Von Mises distortion energy theory. And then maybe a brittle problem. And some of these might be combined. Like I might have the brittle problem with something that's a stress concentration. But that's basically what we're going to do for exam 2. I will also say that like one of my highest priorities is that you have a mastered and continue to work and be able to solve statics problems. So drawing a free body diagram and getting the reaction forces, whether that be in a door handle type of cantilever problem or a simply supported problem. These are my priorities. And so we will have the problems that represent those. And if some things that we didn't really measure on exam 1, you can count on that I'm going to look at exam 1 and go, ooh, I didn't really measure if they could do this, and then I'll put it on exam 2 for sure. But also if people struggled with something, and we did a recoup, so you'll recall that a particular student might have struggled with something, that I'm going to, now that you did it on the recoup, I'm going to see if that had any effect, right? Remembering that the exams are not just to try to torture you, that's just a side benefit, but primarily just to measure your mastery of the material and see where you're at by giving you problems and seeing how you do in solving them. So here is the examples or the problems that I posted. I think I have posted the solutions to these. None of them were my solutions, so there might be some deviations. But this is a deflection problem, and of course this is going to have superposition because there's really 2 different loading cases. So maybe you would find the deflection at B with this. Here's a buckling problem. Requires a little bit statics, right, to try to figure out what the loading is going to be on this thin portion right there. And you have to kind of work backwards a little bit to try to figure out what that load is. So maybe, and you want to look at the end conditions on here. I think you can consider this to be pinned in there. Yeah, I think so. But there's actually two different directions this thing could fail. So you want to try to, think your way through how that would fail. And, we might actually like think about this one. I don't know. In talking about it right now, I could kind of see where you might think about the buckling condition that is out of plane, right? That's going to, because it's the, well, I don't know. Yeah, you can see there's 1.5 inches wide. I think you're going to say that direction right there, and then 1 inch thick. So it's going to probably, chances are it's going to buckle across there, but its effective length is probably cut short because in this type of pin situation, in that plane, it's kind of out. So anyway, it's an interesting problem, but we don't want to go too far down the buckling road because that's not really one of my highest priorities. Here's just a generic problem out of the book, right? So you should be able to do this. And maybe I would save this one to try to see if, how fast you could do a problem, because it's a simple problem, right? So you want to try to build up speed. I see a lot of students are very methodical, which is a great thing as an engineer, not a great thing for a test taker. Here's a problem. This is actually quite difficult and challenging. It has a couple unexpected twists. No pun intended, because there's torque, right? That's sort of a pun. But anyway, so I would measure yourself if you could think through, because it's not a typical problem. It's got some additional things that maybe you might not consider. So we can go over it, but it is a I don't know. I think this was part of a test home, a take-home test, I think, that I had done, maybe. I don't know. Here's a stress concentration problem with combined stress concentration. So one thing you might want to check on part of this is this is a brittle one, right? So because it's cast iron, so you might want to check that. You also might want to check for von Mises and maximum shear stress theory, but this is because it's brittle. You should know that this is a brittle Coulomb Moore is what we will use to do an assessment and a safety factor on this. Pressure vessel thing. I was kind of wish I had some other pressure vessels one on there that had more combined stress type of thing. And we're not going to do any fracture mechanics problems because I didn't assign any homework in fracture mechanics this semester. I have in previous semesters. So if you see other review sessions, you might see some more fracture mechanics stuff going on there. Then here's another cantilever problem, a little more interesting, a little closer to real world. I guess this is supposed to be a helical gear, although it doesn't look like a helical gear because it has a radial component. That's how you know, not a radial component, but it has this, call it I'm trying to remember the terminology. It has a component that ends up being axial, right? It's got an axial reaction in 40 pounds. Here's a problem out of Shams, a 3D shaft problem out of Shams outlines. Another stress concentration problem. So this one's a little bit different. And then an additional stress concentration problem. It's kind of this is a stress concentration set that's available within Shigley. And then I have solutions. So I just wanted to brief go over the kinds of problems that you can expect on the exam, and I will leave the floor open for any, and I'll check the chat for any of your suggestions for problems that you would like to see. I take requests, including, shut up. No, that's not true. Don't request that I shut up. And I have Shigley open or available. I have a file of Shigley open, so we can look through problems in here and also suggest them.
Do you mind doing a stress concentration problem?
Okay. Do you have a particular one in mind, or should we invent one?
Not really. Probably invent one.
Okay. All right. So let's see. Maybe I'll pull up another book, and even though that might not be the same as we have, I'm not feeling very creative today. I should be creative. Here's one of my good buds, Norton. Do I have Norton in here? I bet I have Norton. I like Robert Norton from the Worcester Polytechnic Institute. I like his style, man. He's got some. He's Bob Norton's cool. So I'm not sure what. Let's see. Static failure theories. So let's see in chapter 5. Let's go to the back of chapter 5 and see if we have some cool images are in here of some stuff. Yeah. All right. Well, let's take this guy right here. Let's pretend that he has some stress concentration right here at A and B. So let's see what the see this problem and draw it out, because I always like these kinds of. Let's see. This is 53 through 36. So 33 through 36. Is that what I said down here? It says the data in the rows from table 5.3. Where the hell are you, 5.3? Oh, there you go. Oh, wow. He made a whole bunch of different problems out of the same problem. Way to go, Bob. So let's just go ahead and pick this one right there. All right, cool. So we're just going to pick row A. Let's check them out. And let's get the worst case right here at A and B. So here's the problem, and I will draw it out on my page while I read, if I'm capable of doing this. I don't like his drawing. I wish he'd made like a little better drawings of this, because this is a kind of a. I don't mean to criticize. I'm sorry, Bob. I'm sorry, Bob, wherever you are, for making fun of your drawing. But a little effort, man. Come on. And my drawing's kind of bad right now too, so now I'm feeling guilt for having criticized Bob. So I didn't do a masterful job here. So the force on this is going to be 50 pounds. I'm assuming that's 50. Actually, these are probably millimeters, aren't they? Let me see. What do you say? These are all in millimeters. Okay, so sorry about that. And newtons. So let's go here, and this dimension is A between these two right here. This is kind of boring, so let me put it in my as I go through here. Okay, so here's 400 millimeters in between there and there. He gave us this height of the thing. It's just not really important to us, but I guess we can go ahead and put him in there. Did he? Where is that? Where did he go? Did he put the height in there? Yeah, I did. There's 20 millimeters. Okay. 20 millimeters. Oh, there it was. Okay, so there actually he gives us the thickness of this. So that's 10 millimeters. And the length, he gives us the length right here. I guess we'll go this way. Okay, I'll erase the gap of 100. And anything else? I guess I need the diameter of this is not written down there. Where did they go, diameter? Oh, it's got OD of 20 and an ID of 14. Okay. So 20 millimeters OD. And then I guess I'll just write in somewhere that the ID is 14 millimeters. And we're going to have something right there at the wall. So let's just say that this wall has a fillet type of connection onto it of I don't know what seems appropriate there. Let's go for a 2 millimeter. Nah, let's go 4 millimeter. Yeah. So hopefully that'll be end up with that'll be on our chart. That's the danger of picking on these things. So first things to do, I'm going to go for the geometry. This is usually not something I ask on the on exams because I try to make time savings things. But in reality, in real life, right, we would need to do that geometry first and get that this is OD was 0.02 squared minus 0.014 squared, and pi over 64 0.02 fourth minus 0.014 fourth. I think I have enough room left over there, maybe. And then this is just going to be 2 times I. All right, so I hear a blinky blink thingy. And so let me see what that was. Comcast sucks. I have no home internet right now. Oh, I'm sorry. You can, there's a call-in number I think you can use for this. Let me see if I can make that setting. It has an anonymous dial-in of 571-392. Wait, I shouldn't. We might post this video. So anyway, sorry if you can hear me or see this. This is the call-in right there. But once again, that doesn't make any sense. But anyway, I think that's nobody's going to be breaking in here later on. So I guess it's a silly thing to be concerned of. I can hear you fine. Okay, good. All right. So anyway, let's calculate this out. 0.02 squared, and then 0.014 squared, and we can subtract them and multiply by pi and divide by 4, and don't give myself a lot of room, but I'll get it. I'll squeeze in there. 1.602 e to the minus 4. Those are meters squared. And then still do it again here for the fourth. Boom, 0.014, 4, boom, minus, and then pi times 64 divided. All right. And so we have a very small number here, 5.968. E minus 9 meters fourth, and then 2 times that, and you have 1.194 E minus 8 meters fourth. When it comes to the fillet right here, let's take a look at our stress concentrations for a fillet. And bring him over here, and that's going to be in the appendix. And we're going to come in, and what we need out of this, we need the axial torsion. No, we don't need any axial, right? We don't need axial because the loading condition is only downward right here, right? So we don't have anything pulling in the, let's call it the x direction. We didn't draw an axis on here, but this is the x direction. And I'm going to consider this to be the y direction, and therefore this will be the z direction right there. So we don't have any axial, so we don't have to look at that. That's good news. But the fillet, what we will use for that is this on this table right here. I don't think we've done stuff with this table yet. Maybe I can't recall a problem where we did with this table. So let's take a look at the, I'll go to the bending moment. So we need to have, okay, so for one thing, we're up against a wall. So when we go up against a wall, and I don't think we've done a problem like this, that D is going to be infinite, and we don't have any better information than this D over D is equal to 3. So you might, I know this seems weird, but it's what the book does. Says, well, then just go ahead and use D over D equals to 3. Because these, if you were to see a listing of these, they would get smaller and smaller and closer together. And they start to get pretty close to infinite is now equal to 3 is what I'm telling you. I know, that seems weird. So what we really need is an R over D. And I decided that our R over D, I picked 4. So now it's going to be 4 over 20. And I think I can do that in my head, but I still pulled out my calculator. should be 0.2, dummy. All right, so 0.2, we can see, we really zoom in. We really want to be neurotic about this. We see that 0.2 is going to be under, okay, so right here is 3. Let me, I'll put in my little comments onto the thing. Right there, I'll right on top of this. 0.2 is right here, right? And we could say, let me make that thinner, that 0.13 is right there. Okay, so no, excuse me, wait a minute. This is 1.2. This would be 1.3, and we can see we're a little bit higher than 1.25. Call it 1.26, right? So, but you want to be pretty careful with these. So we'll say that the K, because of bending, and maybe I'll write it over here. I don't know how to go with the bending one. Is, what did I just say? 1.26. But we could go a little bit crazier with that to try to get it, but that's in the ballpark, right? We'll also come up to the torsion one, right? So this is, no, that's the axis. I think I accidentally just did the torsion one. Sure did. I sure did. That's easy to mess that up, so be very careful right there. So double check, and that's what I kind of just did. I caught myself. But so that 1.26 is the torsion one. And by the way, the best we could do is a D over D of 2, because they didn't give us anything else in this type of situation. And here we will pick another 0.2, and we'll use the 3, and we see that. Well, here's 1.6, and so here's about halfway down is about 1.5, and I would say this is just below. That would be my judgment. Maybe I should have made that mark a little bit better. I didn't do a great job of my little mark. So I would say that we're somewhere in there is our 1.5. And I'd say, yeah, we were pretty much at the halfway point. So I'm going to call that 1.45. So for the bend, the KT is approximately 1.45. All right, so we got like the geometry stuff out of the way. And now we want to go to the loads. Loads, wow. Great. Starting off great. Loads. Okay. So generally speaking, we should do an FBD based on this. Zoom out so I can look at this a little bit. All right, let me just proceed. I like to go X and Y first. So an FBD in the X and Y. And because there's only really one load on it, this is sort of just a exercise in being making sure that we're doing the correct routine, right? Honestly, to be frank, this is a little bit excessive, but let's do it anyway. Good practice. I would probably put another load onto this, and I guess I could. Maybe I will put another load onto this thing. Let's get this guy out of the way. I'm just going to go ahead and put another load onto him this way right there. And he's going to be 70 newtons. Let's see if we can break this thing. I don't know if it's going to break or not. But that 70 doesn't show up in this right here. So this reaction moment here at the wall this is going to be clockwise. So this is going to be counterclockwise, and the sum of the moments about the z-axis. And we can easily get this, right? And this distance was 100 millimeters. So I like to keep things in Newton meters along the way. So we're going to say that we have our reaction moment mz minus our 50 times our 0.1. And I think I can do that in my head, that mz as a reaction is going to be equal to 5 Newton meters. I could do it. All right, and then I want to do the top view of this. So in a top view FBD, I would draw it like this right here, and I like to draw them right underneath. I give them aligned sometimes. And in this case, now we're going to have that 70 that's happening right there, that 70 that I just added to the problem. And still, I guess there's really only going to be one moment. So this is actually, I know I didn't really overly complicate this by adding in that other 70, but we can see that we're going to have a reaction force in the z direction, which I didn't draw my axis on there. There you go. Right here. And then in terms of reaction moment, once again, that's going to be clockwise. So this you can predict is going to be counterclockwise, and this is going to be my. So taking the summation of moments about the y is equal to 0. Consider that positive. So we'll take the my and then minus the 70 times 0.1, and this too we can do in our heads. 7 Newton meters. And then the last FBD to do. Are you okay? What's up?
Where was
are we
that?
recording this? I think we forgot to record it. We record it? No, we are.
It says it, yeah. Where
Yeah.
was the? Did you put the? Where do you get the 70 from? Is that in the problem statement?
I just went ahead and added it in just a second ago.
Oh, okay. All right.
Because as I'm looking at it, I'm going, this is a little too easy. I think I'd rather do all 3 planes. So yeah, I apologize. I called it an audible, and maybe I jumped through it too quickly. It would be easy to miss. I know.
All right.
Thank you for keeping me honest there. So anyway, let's see. We'll put these guys on here, and now the 70 will show up. That 70 that we just added a second ago. I wanted to improve Bob Norton's problem right in here, and so this is declare. I like to declare an FBD and also establish. Let's see what our axes are. Helps to keep us oriented. And now we're going to have a reaction. Oh, I drew the arrow in the wrong direction on this one. Shame on me. I like to have them going away most of the time. So I'm going to post them up there. So sorry about that. Let's see. That's an RZ coming up in that direction. So this 2 here goes RY. And I guess I'll have them pointed inwards. There we go. RZ. Yeah. And then we're also going to have a moment that's acting onto this right here. And this doesn't cause a moment, so this causes a clockwise moment. So this is, again, counterclockwise. X, and summation of mx, we'll have mx is going to be then minus 50. And then this dimension was actually 400 millimeters. So that'll be 0.4. And just to double check, I believe that's going to be 0.4 times 50, should be 20. Yeah, 20. I just didn't trust myself to do that in my head. 20 Newton meters. All right. So we got, okay, then one last thing maybe for our loads. Instead of the original problem, which I believe was asking for, they might be asking for specific directions. I'm not sure. Let's see, take a look at Bob Norton's thing. I guess this was problem, what, 33 or something like that? Yeah. He wants to do it. Von Mises at points A and B. I'm going to find the worst spot because that's really what I care about. And if it's the worst spot, it's going to be bending in 2 different axes. So we need to combine MZ and MY. MX, remember, is going to be, that's going to cause torsion. So that doesn't cause bending. It causes a twist of this thing happening, right? So the torsion is happening across there. But we also are making a bending coming downward that way because of this 50, and we're also taking a bending and going this way with the 70 about the y-axis. You can visualize that without even doing the FBDs. But so we're going to say that the max moment is going to be the square root of the 5 squared plus the 7 squared. So to get the out of plane bending moments that we're going there. So it says 25 and 49 and square root. So we get 8.602 Newton meters is going to be causing the bending on this. And maybe the clipboard's just causing me more problems. I do like a good clipboard. Maybe that's a nerd thing to say. I don't know, but I do enjoy a good clipboard. And so here we're going to start with our stresses. And remember, these are nominal stresses because we're going to apply the stress concentration to them. So in terms of the bending, we're going to have, I'll call it nominal. And we're going to MC over I. And the moment to use here is 8.602. The C is going to be 1/2 of the outside diameter. So that's actually, the outside diameter is 20 millimeters. So we're going to go 0.01 is going to be the radius out to the outside. And we found previously the moment of inertia here was 5.968 E minus 9. So that's going to give us quite a bit of stress right there. So let's go. I still have that in my calculator. 0.01. And let's see. Do I have this still in my stack? No, I don't. Okay. 5.968 E9 and divide. Yeah, so I get 1.441 E7 newtons per meter squared. If I divide by 1 million right in there, I'm going to get 14.41 megapascals. And now if I go for torsion, I'm going to get tau nominal, TR over J. And our torsion, we just found out, was 20 Newton meters. We have the same distance to the outside fiber for torsion as we do for bending for a round thing. And we now use 1.194 E minus 8. And what I end up with is 20 times 0.01. Do that in our heads. 1.194 E8 and divide, and we end up with 1.675 E7 newtons per meter squared. So that's, we do that in heads, are 16.75 megapascals. And now we want to find our maximum stresses here. So we take KT and times it to the nominal, and the KT, well, for the bending was 1.45 times our 14.41. So we had 1.45. So we end up with 20.90 megapascals. And then for our torsion, we had, it was 1.26. And I find that's pretty common for the torsion stress concentration factor to be less than the bending. But if they have a bending and an axial, you'll end up finding those are actually pretty close to each other, which kind of makes sense to some extent. So we take that, and I still have that in my stack. So 1.26. So we have 21.11 megapascals. And by the way, this is tension and compression because this thing is, bending sort of, and I kind of drew sort of these little arrows on here, which I kind of saw that the 50 newtons was kind of making a bending that's kind of coming down that way about the Z, right? And the 70 was really kind of making a bend that's coming down about the Y. So the overall bending is going to be down and to the left over here. So there's going to be tension somewhere up here and compression somewhere down there. Maybe I'll make it like right in there. So we're going to have that tension stress in the normal direction here of like 20.90 and compression over here. When it comes to the brittle Coulomb Moore, we would actually want to maybe check both spots, but it's probably going to be the tensions that's worse because the stuff is weaker there. But let's find the maximum shear stress theory and the distortion energy theory results. The best thing to start right here is maybe to draw a little stress element, and I'm going to emphasize that we know this horizontal is in the x direction, but we don't actually know this isn't really aligned with any particular axis because we're actually turning it around and probably looking diagonally at this thing from kind of that direction, right? So neither that way nor that way, but somewhere along that line. But we're going to have a stress that's in this direction right there of 20.90 megapascals, and looking at this torsion right here, we can see the torsion is coming. Now that's going to be around that way right there. So it's going to be crossing the face. So it's really going to be that way right in there for our shear stress if we wanted to get correct. We're not, and as usual in many problems from here on out, we're going to ignore the transverse shear because it's basically fairly small compared to these other stresses in this scenario. But it's worth knowing about it and keeping in mind that it exists. But in terms of our general procedure, we're going to ignore it. So having drawn this out right here, we could do the best we can without graph paper to do a quick Moore circle, and the Moore circle is really is a helpful means of trying to visualize what's taking place. Let's see, I'm going to try to get this correct. I'm going to graph this guy's face first, and this one's going counterclockwise while that one's in tension. So I'm going to be somewhere, and they're nearly equal to each other, so I can kind of graphically maybe I can, I don't know, let's just try to take a look here. I'll use 1 inch as my thing to represent this right there, right? So here we go. Here's 1 inch and 1 inch right there. So this is going to be the point I'm graphing for this, calling this like nearly 20 and like nearly 20 right here for our normal versus shear. And that means that up here somewhere, okay, so I didn't do a great job on picking this graph out right there because it's going to be like right up there. It's also going to be 20. So our midpoint is right here, and maybe I'll call this my radius. And I do have a whole lot of compasses. Compi? What's the plural of compass? I don't know. I took Latin in high school, but I wasn't a very good student. So let's see. Did that come out? No, still, look at that. Very upsetting when that doesn't work right. But I did have a discussion with one of the students the other day about this. Like, don't drive yourself nuts trying to make the thing perfect on an exam. Perfection is a nice thing. It's really nice to have a really good drawing of things, but don't spend too much time trying to make the thing perfect. If in terms of the other 2 more circles that you would want to include here, let's see, you have to monkey around with this. I bet there's an easy way to do this that I can't remember. Let's put that up. There's the other 2 more circles that you want to remember. Basically, by the way, a lot of times I lean to when I'm going to do a maximum shear stress theory problem. I really kind of like using pressure vessels. And I see, now look at the terrible job I did right there. Oh, that's just sad. Okay, but anyway, And it's even sad that I wrote over this right here. This is not, I expect so much more out of you than me. That's not true. But anyway, that's sigma 1, sigma 2, and sigma 3. Now, in terms of numbers, we're going to take the center right here is just going to be this divided by 2, right? Because there's no, yeah, you got it. So 20.9 divided by 2. Should be able to do that in my head, but 10.45, of course it is. And the radius right here, a little bit of a thought process, is we have to do the square root. In this case, it's just the center, 10.45 squared, plus the shear, which is 21.11 squared. So we can go, so square that, and 21.11 squared plus, there, boom, we get 23.56. So sigma 1 is going to be C plus R, or 10.45 and 23.56 plus. So we have 34.01 megapascals, and then sigma 3, excuse me, because sigma 2 is equal to, let's write that, sigma 2 is equal to 0. Sigma 3 is going to be C minus R, or 10.45 and 23.56 subtracted from it. So you're going to have a, I'll call it negative 13.11 megapascals. Just remember, don't put the minus sign and the compression thing, so we could rewrite it out here, just at this point of emphasis that this is the way that you would write it out, but don't put a negative 13.11 and then put compression in there. And we could go ahead and put tension right in there. Okay, so, and then we can get, okay, so the one that we really care about for maximum shear stress theory is this guy. In this particular case, this is the tau abs max, right? Because, you know, we have three more circles, but this main Mohr circle is the one that has a radius, the largest shear, right? So here is a, here are the other maximum shears that could be existing, but this is the absolute maximum because it's on the biggest of the circles. So I'll even write that down. Abs max is equal to 23.56 megapascals. And for the von Mises now, because we have the simplest of condition, not the simplest, but we have a very common condition of uniaxial stress, we can just say that it's going to be sigma squared plus 3 times tau squared, or 20.9 squared plus 3 times 21.11 squared. So our von Mises stress and 21.11. Did I do that wrong? I feel like I did that wrong. I'm going to double check. I got 42.12, but I feel like I made a mistake with the buttons. So I like to double check myself when I feel like I made a mistake. One more time then. 21. How am I doing this? How am I making a mistake? Oh, I know what I'm doing. All right. My brain is not functioning today. 42.11. That's what I had before. 42.12, I guess, megapascals. So if I want to have a safety factor now, I'm not sure what the original problem was saying. I think the original problem, if I'm not mistaken, was just asking for the stresses. They didn't tell us what the safety factor was, but maybe compare appropriateness. Okay, assume a ductile material strength of 400 megapascal. So we're going to be very, very safe. They're going to say that the yield right there was 400 megapascals. So our safety factor for maximum shear stress theory, remember, is going to be the yield strength divided by 2 divided by the tau abs max. Or we will say that it's going to be 23.56. No, dummy, come on. 400 divided by 2 divided by 23.56. So it's going to be pretty damn safe is what it's going to be. I could just 200. I didn't have to do that. 23.56. Boom. So we have safety factor of 8.49, call it, for maximum shear stress theory. And then for distortion energy theory, we have yield strength divided by von Mises stress, or 400 divided by 42.12. So we can expect it to be nearly 10, 9.5, 9.496. Remember, only 2 decimal places, please, for this. So there you go. I did a long problem, but you know what? Usually it's going to be a shorter problem for an exam because this actually took me like 45 minutes or 40 minutes or something like that, which is too long for a problem. I usually try to ask, try to time out somewhere between, I get, like 1/2 of the 75, right? So when I'm doing my timing myself, I try to, what does that work out to? Like 37.5 minutes. Well, I actually been in recent years been trying to get it down so it's like down to like closer to 25 minutes for myself, or 25 to 30 minutes for myself, because I see so many students who don't finish the exam in the time. But let's pick another problem type. Or in that I should ask along. You're welcome to interrupt me. Not interrupt me. That's not right. Just add questions to the chat. Make this interactive as much as possible. Pick another problem out. Pick a problem type.
I actually had one question about this problem. I kind of, so we did the moment maximum of this because we're trying to find when it is max, or when the stress is max. Okay.
Yeah, it's usually the case where we want to figure out where it's going to break, right?
Mm-hmm.
So we want to try to get. A lot of times, the safety factor might be for like a specific spot, like maybe a question. But the truth is, we just want to see what's the worst thing that could happen here. It kind of leads me to also want to mention, just in terms of real engineering, we're only looking at this one spot, but I'm a little concerned about this thing. How thin is this piece right in here? Or what about this joint in between these two spots, right? Is there anything particular about this? And then we also, it would be maybe particularly challenging to address, but what about the buckling of this piece right there in terms of the twist buckling that could happen because this thing's a thin plate? I gotta have some questions about that, right? So when doing an investigation on this, you probably want to try to find out what's the worst thing that can happen. And then overall, instead of thinking of the safety factor as being for a particular location, you can think of the overall safety factor against the failure, right? To try to think of like how can the thing fail, and then the lowest number for any failure that's possible on this would be the safety factor globally that you might assign to the thing to try to report how safe from failure the piece is. I don't know. I figured I'd add that in there. So do we have a particular kind of problem at any, or a particular problem, maybe a homework problem that you were never clear on? Hopefully hopefully we've looked over the posted solutions to stuff and seen where you went wrong, or if you, assuming there was anything wrong in them, and since, you know, and then tried to resolve what they were. So I think it would have been homework 5. Yeah, that's the deflection one. Homework 6. This was the first safety factor one, right? And some stress concentration ones. If I not posted the solution to homework 8 yet, let me make sure that's. I'll get rid of the solution video here. So it's an important thing that we do here. Homework 8 under 370. I think I still owe you the solution, the grading of that. Homework 8 solution. Okay, so that's one that we have. So I'll make it available here. Yes. I didn't see, where was homework 7? What was homework 7? I didn't look at the solution of that too. All right, so we did, so we actually haven't done a 3D shaft in a while. So I'd caution you to make sure that you're able to work through a 3D shaft, right? So what was homework 4? Homework 4 was contact stress and curved beam. So homework 3, right? So we did that was actually too similar to homework 7 or homework 8, in my opinion. Homework 7, I guess. And here's another cantilevered one. Okay, wow. You know what? I'm feeling a little guilt here. I think that we should have had more practice with this type of problem. So let's do another 3D shaft problem, because I'm concerned that we haven't built up those skills. I usually ask them, or try to do a lot more of these, right? So let's try to pick out one. And Shigley has a limited amount, but they have some right in there. So I mean, you can't interrupt, and you can say, well, I would prefer to see a different problem, but I'm concerned on this one. Let me take a look at. Let me do this one. We haven't done a cantilevered one, so this is a very common problem. By the way, I should also point out that here's another this is one that I probably asked on exams before, right? So I don't know how that happened right there. Undo that. But so be aware that, because this one has only one plane, so you don't have to worry too much about it. Just like this one only is only a one plane, so it might look like a 3D shaft, but it's only a 2D shaft. This is a 3D shaft right there, and this is a 3D shaft, right? Because it's going in two different planes. These are ones that or variations like that. Generally speaking, they're a little too much involved, too long to take while doing an exam. Although I have seen professors who have assigned these for exams. So let's do this one on the left, because it has a cantilever problem. I seem to recall this one actually being like the stress of this 1.25 inch being way too small, or it might be this one with the 50 millimeter, it might be too small. One of these two is like really, really bad in terms of the design, and needs to be redesigned as part of this. So let me draw up this problem, unless anyone has any objections. So I'm gonna draw this up. I'll pull this up over to the side and look, and let's see. I'll try to make a nice drawing without taking too much time to do it. But here is what the end condition looks like right here. That's a gear that is kind of cantilevered off to the side. It has a force that's on it, FB, that has it's coming in at an angle. So by the way, this is the z-axis, the y-axis, and here is the x-axis, and that's not the greatest gear looking thing, but it's not terrible, I guess. Here is the bearing that's on here, and that is a terrible bearing. I just did a terrible job of that. Let's see. I'll try to kind of weasel my way into making it look better. I actually do I have my isometric things out here. Actually, I do have my isometric. Oh gosh, I haven't used these in a while. But try to draw in my isometric gears in there, and I guess I'll freehand this one right in there. Try to put him in place. Make it a little better. And then draw this last bearing right in there, kind of like him up there. Not my best work, but good enough right here. All right, so this other force is kind of come in here, so this should be aligned with this. It's also coming in at an angle, because that's how gears work. They have a profile, and that causes. Let's see. I can actually show you right here. I can have it sitting right here. Sorry. All right. I don't have this guy's partner, but I have this little gear right here. But you can see that the gear has to come in and be perpendicular to this gear surface right here. So that's why it's not this way. It always has a radial component. So this angle that would form between here is called the pressure angle. So that's why we have that 20 degrees. Thought it was worth that moment, but I guess not. Anyway. And then this one is also 20 degrees. It's a very common pressure angle. The dimensions that we have off of this thing. Okay, we also need the bearing right here. So we take this, move that right there. And so this is 16 inches, and this is 14 inches, and this is 9 inches. Don't have to draw arrows, but I felt like it. And this thing is a 20-inch diameter. So I'll just put a leader up to there, the 20-inch diameter. And this has an 8-inch diameter. And they said that this has a 1.25-inch diameter. And we didn't do any stress, I haven't done any stress concentrations on this, so I don't think I'll start right now during the review session. But, so anyway, let's see. We'll start out with some geometry, maybe. Okay. Where we don't have to actually find the area, so let's not bother. We have to do the moment of inertia for bending, and so that's 1.25 fourthed, and the J is just 2 times the I for a circle. I was kind of casual about that, but maybe I think that looks like it's probably the right answer. I think I've seen 1 1/4 before. And so 0.2397 inches fourthed right there. Okay, we got the geometry out of the way. I'm not going to include any stress concentration, but let me go ahead and find out what the other load is going to be, because they didn't give it to us. So we want to do a FBD of both gears intact. So we have a force coming this way and a force coming that way. And so this is FB, which we can also note, we could also have put in here. Probably a good idea to go ahead and break these down into components already, right in there. And so the truth is, I'm going to do that, I'd probably be best not to draw that in as a full force because I don't want to make it look like both forces are on here. I'd rather have an FB, call it Z, and have an FBY. And then the same thing true with this. I won't put that guy in place. I'll put him as a ghosted or a hash line here and call this one, because what do we call this? I guess this is O, A, B, C. So this is F, A, Y. And this is F, A, Z. And F, A, Y is equal to our 300 times the cosine of 20. F, A, Z is equal to 300 times the sine of 20. And 281.9. It just occurred to me that this is very passive for you to be listening to this. So one suggestion that I would have, and it might be, I don't know, maybe be helpful. Something that I had tried to do as a student was to try to race the professor sometimes, right? To try to keep up, maybe not to write down what he or she is doing, but to try to anticipate and see and use my calculator along as I'm going through. Instead of just simply listening, I find, you want to just avoid the transcribing and you want to avoid just the listening. So try to beat me to the punch, right? And see if you can outrace me and catch me in a mistake. I don't mind. I don't mind you showing me that I'm a screw up, right? It's totally okay with me. It's not about me. It's about your learning. So I've just mentioned that in terms of like the how to get the most out of classes and exam prep or whatever is to try to see if you can be as active as possible in your approach. And I should try to encourage you to do that as well. So anyway, we'll take the sum of the moments about the x-axis, which is coming out of the board to us. And so clockwise is going to be the FAY that we know, and that's 281.9. And its moment arm is going to be the radius of this, which is going to be 10 inches. And in the other direction here, we're going to have positive FBZ, which we don't know, which is being applied to the radius of this, which is 4 inches. And so we'll be able to get FBZ from that. And so that's 281 times 10 divided by 4. And we get that that's going to be 704.8 pounds. And then from the angle right here, we could also find that FBY is just going to be, let me think this through right here. This is the run, and so we can get the rise by taking 704.8, that's a 4, and multiplying by the tangent of 20 degrees. And we get 256.5 pounds. Now we're going to need to know what the torque is in between this gear and this gear. Remember, the torque is going to be 0 out here, but there's a twisting that's going on in between these two. So I draw another FBD and kind of didn't plan out my page very well, but we could do either one of these. I'm going to go ahead and cut it right there. And so we're actually revealing inside the shaft to try to expose. And I'll put in these these guys right here. I already know these values, so I'll put them in here. Here's 102.6 pounds, and right here is 281.9 pounds. And that's going clockwise, so the internal torque, at least from this perspective, is going to be counterclockwise. So summation of moments about the x again is going to reveal that we have a torque minus 281.9, and that's times, did I do that incorrect? No, it's going to be times 10 again, right? Because it's just the radius of this. It's equal to 0, so the torque is going to be 2,819, right? And these are inch pounds. So now we're ready. We're prepared to approach the bending portion of this. By the way, I didn't label this, but this is the loads portion that we did right there. We're still in the midst of it. And this problem is too long to be able to do this. So in times where I have had 3D shafts, what I would do sometimes is already give you one plane, right? So I would make both the shear moment diagrams side by side, and I'd give you all this stuff in one of the shear moment diagrams to make it just to try to reduce the amount of time that it took on an exam. Because I really do want you to demonstrate that you're able to do one of these problems, but quite often the time crunch is really the thing that's kind of like hitting us in the head. Which is kind of a mean thing. So why did I say hitting us in the head? That's a lot of violence. Too much violence. It's too much violence. But anyway, I'm going to draw this thing out. And sometimes I'd actually draw out the side views for you. That that's part of that as well. And herein lies some differences that we're about to run across between previous problems, because we haven't really done any that were cantilevered. So the shear moment diagram is going to look a lot different. Not a lot different, but it's going to have some different peculiarities. So if we haven't done one along those lines, experiencing it for the first time during an exam isn't exactly ideal. That's what we're saying. So let's take a look and apply the loads right here. Remember that this is O, A, B, and C. And while I'm talking about it, let me go ahead and label this as 16, 14, and 9 to help me orient myself. But now I want to look, and now, so this is going to be the Y direction, and this is the X direction. This is the Z direction, and this is the X direction. So looking from the side up there, I'm going to see this 281.9 coming upwards. And I like to kind of draw it where it actually is right there. So that's the 289.1 pounds. And then from the side, we're going to see the Y component of FB, which we found to be 256.5. So that shows up right here. 256.5 pounds. And then looking down at the plan view of this, we would have the Z component of this, which ends up being 102. And it's going to show up right there, 102.6 pounds. It doesn't matter to us, at least, that it's here rather than there, but I just kind of like to make it as best I can clear that that's what's actually taking place. And then lastly, we want to have the plan view of this guy, which is the Z component with a 704.8. And this is probably gonna, this is like the largest force that we're seeing here in any particular plane. So he could be significant to us. All right, so drawing the reactions of this could be a teeter-totter situation right in here, right? Because this one wants to make it go that way, and that one wants to go the other way. I'm going to think that this needs to be up in that direction. And this is the RBY. And I think because of this teeter-totter situation here, we're going to have our reaction at O that way. That's my prediction. And I might need to use another sheet of paper to do my, instead of trying to cram it in there, to do my statics. And this guy right here, he too, I think, because he's so large, needs to have an reaction going in the opposite direction from him. And he's so nearby each other. That's my mindset, at least. And then you can think of this thing as trying to teeter off of here. So I believe he also, this guy needs to also be downwards right there to prevent it. So yeah, so we're going to have an R-O-Z, Roz. And he's kind of, I kind of drew that a little deep, so I'm going to try to move that down there. And then, so therefore, this one has to be somewhere in there, right? So this is V, M, V, and M. And I should label what these are. I like to use brackets for the units. All right, so I'm going to do statics. So I move the page right there. And take the sum of the moments about O equals 0. And this is very, very important to me that you're able to find these reactions and get them reliably, right? So make sure, if you can't do this yet, that you follow along what we're doing here and make sure that you do practice problems where you try this out for yourself and get it down to you're really a master of it. So we'll start out with this guy. He's counterclockwise about O. So he's 289.1, and it's going to be 16 inches away. Here, this guy is also counterclockwise, RBY, and now he's going to be 16 plus 14, which I think is 30. I think I could do that math. And now this guy is actually clockwise, and he's 256.5, but now he's going to be 39 inches away. And once again, I had to assume this was going in that direction. Hopefully my math works out. So 289.1 times 16, and then we're going to subtract out 256.5 times 39, boom, and subtract out. Sure enough, we got a negative number. That's good. That means, because it's going to jump over the other side, so it's going to be positive. We divide by 30, so we got RBY as being 179.3 pounds. And then do sum of the forces in the y direction equals 0. Upwards is positive on this diagram. And then we start looking there. Well, I'm predicting this one is downward, so I'm going to go ahead and put Roy as negative, because I drew it on here as negative. I'm going to put negative there. This is positive 289.1. This is also, I said it was positive 179.3, and now this is a negative 256.5 equals 0. So Roy, if you're listening, let's switch that back over to positive. And the 289.1, add them together, subtract out 256.5. Okay, we got a positive number, so that's good because that was going to come back over the side. And we have 211.9 pounds. Doing the same thing over here. Sum of the moments about O equals 0. And this is going to be counterclockwise, so he's positive. 102.6 times 16. And also positive is our RBZ, ribs, and that's going to be times 30, 14 plus 16. And then this one right here is a 704.8, And he is times, once again, that's going to be 39, right? 39. So RBZ, and so we go 102.6 times 16. Yes. And subtract out 704.8 times 39. Boom. Yes, we get a negative number. It's good because that's going to jump over the side. So we chose correctly. Divided by 30. And we get 861.5 pounds. And then some of the forces in the z direction. And I'm going to be technically correct by saying downwards is positive here from this viewpoint. And so that means we're going to have our ROS is drawn in the positive direction, minus 102.6 in that direction, minus 861.5, and then plus 704.8 equals 0. ROS is, let's see, 102.6. I'll subtract out, and then I'm going to add 704.8. Yes, so I get a 259.3 pounds. So now we proceed with this to label. What's going to happen here is over here on the left-hand side, we have Roy of 211. So I'm going to pick like right there. 211.9. He's negative. We're going to come up 289. So 289, 289.1. So we get like 77. It's going to be very small, but it's a positive number, right? 77.24. And then we're going to go up even further by adding in 179.3. And so we go up, and this better be equal to 256.5, and sure enough it is 256.5. Because that's coming downwards, and it needs to bring it back to 0. If it doesn't go back to 0, you did your statics wrong. And now we can find what the moments are going to be, right? So the moment here is going to be a negative moment equal to the area within here. So 211.9, negative 211.9 times 16. We have 3,390. And now we can go either direction with this, but I'm going to go in this direction right here. We're going to go 77.24. So 77.24 times 14. But that's going to be, the other one, this is negative, this is going to be added to it, right? So in fact, it's subtracted from it. So we're going to get, for the other one, all right, still negative 2309, 2000. So we're going to come down to right there. And then lastly, this better come back to 0 here at the at here, because this thing can't sustain a moment, right? So there's going to be a moment right to there. But we can check that. It should be 2,309. Check that by multiplying 256.5 times 9. And yes, we get the same thing, right? So we know for sure that we got it right. And that's a good way to check. It doesn't take too much longer to do it. Okay. But if you were to cheat, all you had to do is write that right there times 9 and to get that number. Same thing, do the same thing over here, where we take our 259.3, and it's coming downwards. So this is actually positive in the downwards direction, so 259.3. And then we're going to come up, but not much. Well, just maybe a little bit. 259.3 and 102.6. So we're going to go, not going to make it all the way back up. It's going to go right there. And we'll go 156.9. And then RBZ, which is 861.5, is going to go the other direction. And by the way, it better be equal to the 704 point here, but let's double check. And we have 156.7. Let's go 861.5 minus, and ooh, I made a mistake then somewhere. That's not good. Okay, so we have to do a little bit of backtracking here, but that's not a problem. Probably made a numeric mistake. That happens. 4.839 times, subtract out, we get 30 divided 861.5. I believe that's true. And then we have 102.6. So 102.6. Subtract out, and then subtract out our 704.8. All right, so what did I do wrong? All right, let me double check. I went 259.3, and then 102.6 added. And I got 156.7. And then I subtract out 861.5. Yeah, okay. All right, good. It came out. I don't know what I did wrong there, but I got it. Yeah. But it's good to try to double check yourself. All right. So let's see. 259.3 times our 16, and we should get 4,000. Oops. So 4,149. And then it's actually going to get a little bit larger because this was positive, and that's still positive, so it's going to go up a little bit, but at a different slope right to there. So we could say that we're going to have 156.7 times 14 and add it in. So we end up with 6,343. And then this better be equal to 704.8 times 9. 704.8 times 9. Yes, certainly does. They're equal to each other, so it needs to come back. All right, so let's see. Yeah, I know this is a long problem. So we want to find the maximum bending moment that's going to take place. Is either going to be here at this gear or here at this bearing. I'm guessing it's at this bearing because you'll take a look at how large that is compared to, but well, let's see. It's going to be this and this put together and that put together. So the moment at A is going to be equal to the square root of 3390 squared plus 4149 squared. And I wish that was still in my calculator, but it's not. And 4149 squared plus square root. So we're going to have a 5,358. So we already know that it's going to be this. This is going to be the worst case right there because that's already bigger. But let's take it back in. So that's going to be MB. square root of, was that right? 2,309 squared plus 6,343 squared, or 2,309. Boy, I really feel like I'm just talking to myself. Sorry. Don't worry about it. I'm not upset. I just wish, I don't know if I'm being effective in this review. But anyway, all right, so we finally done with all of our loads portion of it, and boy, did it take a long time. But we can now go to the stress portion of the game show here and find what the stresses are. So we're going to start with the bending. And that's, I don't know what that doesn't mean anything. It's going to be MC over I. And we're going to use, because this one's the max, we're going to use the max 6,750. And the diameter of the shaft is 1.25, so divide that by 2. And we found the moment of inertia a while back of 0.1198. So in terms of stresses, 1.25 times 2 divided in 0.1198 divided. Actually, this wasn't terribly bad, but it wasn't great. Of 35.22 KSI. So I just divided by 1,000 in my head. All right, so there's bending, and then we go for torsion. And the tau is going to be TR over J. And the torque we said was 2,000. And by the way, that's in between, right? So it's we're definitely, the torque is inside the same place as the bending. And so the torque was 2,819. Once again, 1.25 over 2. And the moment of inertia, polar moment of inertia, was 0.2397. So what we're left with is 2,819 times 1.25 divided by 2, boom. And then 0.23, that looks like a 9.7. And we have smaller torque. That happens a lot in these problems, that we get a smaller torsion shear. But if we were to take a look at a stress element, I don't really care about which direction you draw the shear into this. It doesn't really matter, but labeling it to help us think through what our situation is. And then we can move on to our maximum shear stress theory. We could just use an equation. I just think it's pretty much easier to just sort of like accept that you're going to draw in a diagram here. I really think it's easier to do this than to look up the equation, to tell you the truth. But you know you're going to have the abs max like right up in there. And this is the guy that this is the one that we want for our maximum shear stress theory. And so we can find the C by taking the 35.22 and dividing it by 2. So 35.22 divided by 2, boom, we get 17.61. Find the radius, easy enough here. 17.61 squared, 7.35 squared. 7.35. 19.08. And you can almost not even bother with the other parts of it because you don't really even need them, but doesn't hurt to take this and add them together. And find that that's a 36.69 KSI. Principal stress 1. Principal stress 3 is C minus R. And you can say that that's going to be, what's the center, 17.61. And we multiply, we get out rid of the 17.08 and subtract it out. So you're going to have a negative 1. No, I might have done that wrong. No, that's right. No, that's not. Looks right. That's right. So a negative 1.470. KSI for that. But this is the one we really care about because this is also equal to tau abs max based on here. And while I'm here, I'll do the von Mises square root of sigma x squared plus 3 times tau squared. And so we'll say 35.22 squared plus 3 times 7.35 squared. So von Mises 35.22 squared and 7.350. I don't need to put the 0 in there, that was silly. And so you're really getting close to this, really didn't change it much, 35.98 KSI. And I don't know, let's see, what material we necessarily wanted to use for here. Well, let's use A36 steel with a yield strength of 36 KSI, right? So the distortion energy theory says that the yield strength divided by this, and you can see that, well, we're going to get really close. It's really going to be 1 point something. 1.0 and 0, right? So it's just barely making it, whereas the maximum shear stress theory says you take the yield strength divided by 2 and divided by the abs max. So we have 36 divided by 2, and now we have a 19.08 abs max, so it's going to fail, right? Because you're going to take 18 and divide it by 19, basically. You're going to have 0.9, call it 5. It is 947. I only want to see 2 sig figs. I mean, excuse me, I only see 2 decimal places. In this case, 2 decimal places is 2 sig figs. All right. So anyway, we could even look this up and see if we got the right answer. I don't know if I want to do that. Do I really want to subject myself to that possible humiliation? I'm not afraid. Let's see. That was Sigley's 10th edition. And it was, okay, so it started out as problem, let's see, what did we say? This was problem 370, 372, right there. And they actually have 372. Where you at, man? What page am I on? Oh, we got a lot of pages to go. I don't know if I want to show this on the internet, but anyway, there's your 19.1 maximum right there. So there's the principal stresses that they got. So we got the right answer. And you can see that there's their shear moment diagram. And let's see, did I get the right? Let's see. 6343, yeah, boom. So you can see there's an example of a problem and us solving it. And the way that Shigley usually does these things right here, like if we looked in chapter 5, which is what we're covering right now, and we look in the problems, I could actually probably just find it right here and go. They'll say resolve problems. There you go. They cheat right here, and they said, well, problems 3. So this is actually problem 543 out of the book. When they say use 1018 steel instead, so we want to find use both the maximum shear stress theory and the distortion energy theory, and then to compare the results. So this is chapter 5, and they don't bother to resolve things. So problem 543 out of the book, and as you watch my Word document come back from there, I don't know what's going on. Why is that? Oh, there you go. Oh, yeah, it's loading up right now. There you go. So 543. Where'd you go? Yeah. So 543, table A20. stated plane stress, and okay, so they had a yield strength of 54, right? So, and then they never gave us an answer actually, but they decided to use. Interesting here. Oh, I see what they did. They used a different equation for that, but they got that. We got the same thing. Trust me on it. There you go. You can trust me. Let's see. We have someone has blooped. What happened here? Am I in two different things at the same time? How is that possible? Anybody said I have to leave for an appointment? Okay, James. Thank you so much for coming by. Hopefully this was somewhat helpful to you. We'll keep recording. We have another 20 minutes left. Let's see. We have Joe and Mikkel, right?
Yep.
You guys got any questions? I can take requests. I can pull my guitar out, start playing a couple tunes.
Well, you said that bending was probably not going to be on the exam, right?
Say that again.
You said that bending was probably not going to be on the exam.
I think you might mean buckling.
Or yeah, buckling. Yeah, I meant buckling.
No problem. No problem. I don't expect it to be, but it is. It's something I want you to know. It's just that I just, got to be honest with you. It's not my highest priority.
All right.
But I might ask a question that wouldn't require. I have considered asking questions that didn't require you to do the calculations, but to tell me, just what are, what is the weak axis or something along those lines. I've considered doing that before, but most of the time I end up just like taking the test myself and going, yeah, that's going to take too long, and then getting rid of the extra question. Just full disclosure. Mikkel, you said that you had a question. Well, at least you said yes, or unless you meant that you're still here as a yes. You could text it if you want, if you have a question, just a suggestion or something along those lines. We haven't done a pressure button, so maybe that's okay. Go ahead. I'm sorry, Joe.
I was also going to say deflection, or is that going to be like another one that's like we might see it?
I have asked. I one time I wrote a question where I was thinking of doing it. I had asked a question like list something along these lines right here. So it didn't require you to do a lot of time onto the thing, but I was like, I had a little piece, little doohickey thing, except drawn better than that. That's just kind of sad right there, just by the way. I mean, at least from my own standards for myself, I'm not going to pass judgment, So I could kind of give you sort of an idea that it went up and there and over in terms of like this right here, right? So it's not too much different from when we had the thing. And I said like, okay, if it has a force right here, make a list of all the ways that it would deflect, right? And it was like really similar to like the homework problem, but maybe just with a little bit of difference. So you had to kind of think. So like maybe and if we labeled this A, B, C, D, I would say maybe it was bending. And I ask you for deflection in Y direction, right? So make a list right there. And I could do any combination here, by the way, but so bending of CD due to F, right? So we would have like, and I didn't ask this, but like, we would say that like that right there, that's what we're saying is I'm doing right there. So I didn't ask you to make this drawing right there, but you could kind of see that this was C and this is D, that you'd have that deflection. I would say also, I would say bending of BC due to moment caused by I don't know. I'm trying to think of how to phrase the thing, but what I'm essentially saying is this guy is placing a moment onto here, so that's going to make this guy bend over, right? This force right here is causing a moment about there, and so caused by F times L CD. And then trying to think of another thing. We could also say 3. Here's a little thought of one, is that we're going to have axial deflection of BC due to F, right? Because the F is right here, BC is going to stretch long. That's going to be a really small value, but it would contribute to it. And then like maybe the fourth one would be twist of AB due to torsion or torque. And once again, that's going to actually be the same moment is going to be causing this guy right here. So I have asked something like that before, and then I went and took the test myself and found that, you know, it was kind of getting longish, so I turned it into an extra credit problem. But I might be able to find some combination of other problems that check off my priority of things I want to see that you're able to do, and then measure my own, you know, test taking time and go, hey, I think this can fit within a reasonable test taking time to be able to ask a question like this, because this is actually my priority, recognizing this way more than finding the numeric answer, because finding the numeric answer would takes way longer than I think is justifiable by the justifiable by what I want to measure. Yeah, I think I said that wrong. Yes, hopefully you get the right idea. Does that make sense? Will there be any
Yes.
curved sections in there? I don't think I'm going to do any bent curved beams, even though I don't think we did it on exam 1. I can't remember back to exam 1. It seems like it was a long time ago. Right? Where was so we have exam solutions. And yeah, we didn't do any curved beams on there. So in exam 1, we did a door handle. We did a pressure vessel, right? That's what this one was. And then we did just a 2D shaft, which was very similar. I think this problem was very, very similar to, not you. And we're going to go back to chapter 3 stuff. Very similar to this problem right here. In fact, I seem to recall like saying, I'm just going to make this, use this problem, but make it give you more information on it. Which is, by the way, you know, notably, here's another problem I would practice right here. You could set these things up for yourself and try to pick out a problem that you could invent that's along those lines. Like, you know, here's like a basic problem. Here's a basic problem right in there. And by the way, some of these have the answers in the back. So if you want to try to invent something to test yourself in addition or instead of maybe to the problems that I have in here, I think it's a smart thing to do. But here's the problems that I have to try to help you to assist you in starting. Oh, here's a pressure vessel problem. I'm not sure if I solved that one or not. I think I call this pressure vessel 2 problem 2. Yeah, but that's like a very long problem. but it's from another mechanics and materials book. So be sure to check that out. And I think I've already posted the solutions to these things, right? Yeah. I need to make prettier ones because that's ugly right there. Oh yeah, I posted the solution manual one for that. So anyway, you guys have, oops, did I just, no, I'm still in here. Okay, cool. Wow. Started to think for a minute that I just closed out the review session. We got a couple more minutes left. Do you have requests? You want to do a quick pressure vessel problem?
Yeah, I'm fine with a pressure vessel problem.
Okay. Let's see. Let's think one up. Let's say, kind of imagine a scuba tank, right? And how big is a scuba tank? I guess it doesn't matter how wide it is, but I think a scuba tank is probably less than a foot, right, in diameter. Like 10 inches, 8 inches, something like that. What do you think? Let's go with an 8-inch diameter. And what do you think the wall thickness is? What do you think it'd be? 1/8 of an inch, 1/8 of an inch, maybe? I think so. Certainly isn't 1/4 inch, but let's try 1/8 of an inch. And let's say that some maniac, for some reason, has decided to, I don't know, hang it from the rafters, and then suspend some kind of load on it that weighs I don't know, 1,000 pounds, just to give us some extra weight or something onto the thing. So and then this has a scuba tank. Let's say that he has been pumped up to a pressure of 500 psi. That's a lot, but I don't know if that's a lot for a scuba tank or not. I don't have a lot of scuba tank experience. Scuba Steve. All right. So in terms of the geometry that we would have of this, trying to find, we would first off want to check and see if this is thin walled or not, right? So we know that's 0.125 and for the thickness here, and so the outside diameter is 8 inches, so that the inside diameter is now going to be what, 7.75 inches, right? So the outside radius is 4 inches, and that's going to be good enough. So let's take our T over R and just use the outside radius. So 1.25 divided by 4. I think this is going to be a thick walled. I think I chose poorly because I'd rather have a thin walled. But let's say, yeah. So no, I think I'm okay, right? So yeah, no, that's totally fine. So this is like 3.125, right? So that's less than 0.1, therefore it's thin. It might be too thin. So we're going to have a hoop stress of P times DI over 4T, no, 2T. And longitudinal is going to be P DI over 4T. The longitudinal is always less right there, right? So we're going to have our 500 times our 7.75. That's not a negative there, I just said stray mark. And 2 divided by 0.125. 500 times 7.75 divided by 2 divided by 0.125. So that's like 15.5 KSI. And honestly, we could just multiply it by 2 down here because there's really no difference. That's a 4. Divided by 2. I almost said multiply by 2. So 7.75 KSI. But some maniac has hung this thing off of here. So we need to find, probably needed to do this in the geometry section that I was calling geometry. But I forgot. Find the area and take pi over 4 and outside diameter minus outside squared minus inside squared. There you go. I forgot for a minute. So 8. I should be able to do that in my head. 64, dummy. But the 7.75. Yeah, we need to square that one. Okay, minus. That doesn't seem right, but it's okay. Let me try to keep going. Boom, times 4, divide. And that seems like a lot. Let me try it again. 64, 7.75 squared minus. All right, got the same thing. All right. There's a lot of area. 3.09. So it's actually not going to even hardly affect it. I would have probably needed to choose a bigger value because this is going to be a small value. It's going to be sad. So let's make it 10. Let's make it 10,000 pounds. It's still not enough. I just changed the problem here. So the axial stress on this is going to be that weight divided by that cross-sectional area, right? And so we have the 10,000 divided by 3.93. So we still only get 3.234 for KSI. And so now a stress element on this does have stress in the other directions as biaxial stress. And if we're going to call maybe that X and this Y right here, so we label it X and Y, this will be the hoop stress of 15.5 KSI. And then this stress in the Y direction, let's see if I'll give these guys some names, is going to be equal to the longitudinal plus the axial combined together, or 7.75, and they're both in tension, so they add together 3.093. Sometimes what I'll do is I'll put a weight on top of this thing to try to crush the thing down, or I'll put like a twist onto the thing to make it give some kind of amount. But anyway, adding those things together, 7.75. You add them together, and it's still just 10.98 KSI. So if you do a more circle of this, remember that they're shear, so they actually get plotted onto here. So let's see, we can maybe do a little bit of accuracy here if we use inches in here. So we'll say that here is your 11 right in there, and then this is going to be 15.5. So there's 5, and there's like right in there. So here's our itty bitty more. Here's our little more circle right there, and that's going to be sigma 1, and that's going to be sigma 2. But then we have a bigger more circle. Ooh, kind of fine. There's got to be a better way to do this. Yeah. Oh, and I just picked them up. Let's see if we can get this up there. And then smaller one. Come on. Kind of like that. There you go. Sorry about that. But truth is that we didn't even need to know this, because this tau abs max we could recognize is really just going to be sigma 1. You know, well the equation is sigma 1 minus sigma 3 divided by 2, but sigma 3 is equal to 0, so it's really just going to be 15.5 divided by 2, right? Which was actually, we already knew that, right? 7.75, right? So if we find the maximum shear stress theory, all we had to do was look onto there. So actually putting this weight onto the thing still wasn't enough to affect what the results were. What we would have to do for that weight to even matter in terms of what we were looking for is it would need to be so large that it would make this total larger than the hoop. And so to move this point over to here, and then it would affect the tau abs max. And that's not necessarily like, that to me at least doesn't seem like it's as, let's call it, I don't know how to say it. It doesn't seem as intuitive, like that it wouldn't matter, but it's kind of, we could prove it to ourselves that it would matter. And it's really kind of related to, well, it's related to Moore circle. So anyway, I think I have a couple of people that might come by here in a couple of minutes, so I need to sign off. I hope this was helpful. It's recorded, so those of you who weren't able to attend but can hear the recording, I hope this has some benefit to you. I would also point out, for those of you who want even additional assistance that haven't maybe noticed it before, be aware that I also have this Friday recitation, statics and mechanics and materials help, and they were all recorded, and some of them had like various scans of different things, so you could just kind of like look through there. Like here was a problem I made up one time, and I think, so I'm not even sure what session that was, but that was like session 4 from last year. Those things might be helpful to you in terms of additional problems to try out or to observe and be helpful. So I hope that you will never feel like you didn't have enough example problems to try to get ready and prepare for an exam. Thank you, guys. Have a great weekend. Thank you.
Thanks. Bye.
Thanks, Jeff. Bye.